All right, everyone, we are going to go into our next piece of analysis, which is ANOVA, analysis of variance. Now, ANOVA analysis is really, really, really important. It's becoming a much more popular analysis tool. It used to be a very popular and predominantly tool in biology, but now it's becoming extremely popular, even for especially for mechanical engineers. And it's an analysis tool that allows you, when you have an experiment, let's say I have some outcome. And let's say my outcome can be, let's say I'm measuring temperature. And let's say I'm doing a manufacturing process, and let's say I'm changing my tool type. So it could be, I can have a type that's titanium, I can have it a carbide, a steel. And let's say I'm also changing the geometry. So I'm doing like a mill, I'm doing a drill bit, I'm doing, something else. And then finally, maybe I'm changing like the spindle speed. So I'm saying 1,000, I'm saying 2,000, I'm saying 3,000. And let's say I'm doing an experiment where I pick tie with a drill bit at 3,000 RPM, and I record temperature. And I want to see, well, each of these variables, these are three variables, and I want to see what are the variable effect on my outcome. Now, within each of my variable sets, there's multiple conditions within each of those variables. Now, if you were trying to do this and look at, you can do correlations, we can do t-test and do comparisons, but how do we actually tell which variables, especially when you're running multiple variables at the same time, which of those are statistically significant? So we want to know what is statistically significant. We want to know what variables are large, and what set of conditions is going to allow us to either maximize or minimize our outcome for our best outcome for our experiment. So to do that, we are going to do ANOVA. And you can do one-way, two-way, three-way ANOVA. The one basically refers to variable sets. So it just depends on your experiment. So let's go ahead. We're going to run some ANOVA. We're going to go through some of the background, and we're going to look at an example. And then most importantly, we're going to be able to determine and analyze what's going on in this ANOVA table, because that's really important. So let's go ahead and let's look at a data set. This is a very classic data set, and actually I'm not going to make the same mistake I did last time. So this is my data, and it is looking at basically crop yields when I'm varying the density of my crop, the block, basically where the crop is planted, and then the fertilizer type. So let's go ahead. Let's look at this data. And I can say, let's go, just thinking. It's waking up. And then I think I got it. Excellent. So this is my data set. And when you're doing an ANOVA, there's several critical values that you need to calculate. Now, I want to be very, very clear. We are not going to be calculating these each time. Instead, we're going to use the built-in ANOVA function, but we want to have some checks to make sure that we know what's going on here. If we want to we're going to look at first the sum, essentially, of some general observation or an outcome for a treatment or variable set. So we're going to do one-way ANOVA. Let's look at the sum, basically T, the sum of squares, of the yield values for all of the experiments. So that would be this right here. So we would look at basically this, and we can actually calculate essentially that overall sample mean. So we can kind of calculate that here. It's just going to be the mean of all this data. And this would be my Y bar here, the overall sample mean of this. Now, the sum of squares, you can see, it is going to basically say, well, for each condition, this A is a variable. So for each condition K, I want to take my number of measurements times the average of that particular condition minus the overall average, and then square it. So that's the sum of squares values. Now, I'm looking at, basically, we're going to calculate it first for fertilizer. Now, if you look at fertilizer types, there's really only two types, 1 and 2. So fertilizer type 1, fertilizer type 2. And you can actually see that, 3, fertilizer type 1, 2, 3. And we can actually look at that here. So for example, 1, 2, 3. Those are all the different types of fertilizer type. I'm just grabbing all of my rows in my third column here. So I'm going to run that through. So I'm going to extract the data, take the means, multiply it, and then this will give me my y sub i's. So those are all just the y sub i's that go into here. This is my n sub i's, equal measurements here, important later. And this will be my sum of squares for my variable a. And I can do the same thing for my error sum of the squares. So you can calculate these out. This is an important parameter, degrees of freedom. Degrees of freedom are just going to be the same that we've dealt with previously. So it's just going to be number of conditions, which is 3, 1, 2, 3, because fertilizer type 1, 2, and 3, minus 1. And you have your error, basically degrees of freedom, which will be the total number of measurements minus basically your values of k. So 3. I can calculate mean square, f values, all these other good things. And we can calculate those and we can show those here. And you can get some of those values. Now, I don't want to do this each time. Instead, we have some really nice built-in functions, and the MATLAB has the same thing as well. And we're going to use basically needs ANOVA. So we're going to take our data file, and what we're going to do is we are going to take data file here. I'm getting all of my rows in my third and my fourth column. So you can see here it's just giving my fertilizer type and then the associated yield with it. If I run an ANOVA with this, it will show me for that single variable, and you can kind of see here, model refers to the variable, degrees of freedom 2, makes sense because like we said before, that's the value, basically the number of conditions minus 1. The sum of squares value is 6.6068, fantastic. The error sum of squares is 35. The degrees of freedom there is 93. And you can kind of see that our values all line up. Now, the important thing here is, what is our p-value saying? Our p-value is less than alpha, which is 0.05. So this variable is statistically significant. And that is extremely important. So when you're reading these tables, you want to double check with that, make sure that it's reading it correctly. This, I think, is the key one here. You can kind of quickly check. If it's really something that's very strange, you may want to kind of check here. You also might want to check in here where, look, it's telling you essentially, let's see, 177.01. That's equal to our mean that we got over here. So there's a couple ways to check and make sure your code's not doing anything funky, but we know this is p is less than alpha. So that is a very statistically significant variable. Fantastic. But we need to ask our other questions, which is this variable large, and is there any condition that is statistically distinct from all the other ones? Well, let's go ahead and let's go through that. Let's answer, are they statistically significant first? Well, in order to do that, you can do a post hoc test called Tukey. And you can kind of see that shown here. The Tukey post hoc test assumes that we have the same number of variables, so that's not really what we want to do here. So instead, what we're going to do is a Games-Hal test. And a Games-Hal test is literally just looking at our t-test. So I'm going to go over here. I'm going to go to variables, or not variables, excuse me. I'm going to go to fertilizer. And all I'm doing here is just extracting the fertilizer type 1, 2, and 3 data set. I'm putting it in here. We can look at this box whisker chart right here. And I can see from my notches, which are 95%, it looks like, it's hard to tell. It looks like 1 and 2 may be the same. Maybe 3 is statistically significant. But to do that, we can just do a t-test comparison. And we can see which value is less than alpha. So this is 1 versus 1, 2 versus 2, 2 versus 3. So this is, I think, 1 versus 2. And we can double check that. That is not statistically significant. But 1 and 3 are statistically different. If we look at here, 2 and 3, are just, it looks like just a little bit. Actually, let's go ahead and let's pull this out. Let's do 2 and 3. Yeah, we're just, 1 and 3 are definitely statistically significant, but 2 and 3 look to be over. I mean, just barely overlapping. Actually, no, 0.05. What am I talking about? Excuse me. Yeah, so what's the point of doing this kind of games how calculation, this t-test comparison? Well, if I asked you, what fertilizer type would you use to maximize crop yield? The answer here is 3. Now, if 2 and 3, if that p-value was greater than alpha, then they are not statistically distinct, and you'd have to say 2 or 3, as long as they're both statistically distinct from fertilizer type 1. So that answers the question of, okay, what would be the set of conditions that would maximize yield? Another critical analysis is this partial eta squared. So my partial eta squared value, we can kind of see if my partial eta squared my eta squared value is 0.14 or greater, that's a large effect. Between 0.06 and 0.14, medium effect. 0.01 or lower, small effect. Now, you may be asking, what if it's between 0.01 and 0.05? This is the literature, so you can kind of say medium, small, medium, whatever you want to kind of say. But we can go back through and we can see I'm going to take my sum of squares divided by my sum of squares plus the sum of squares of the error, which you can see there. And my value is 0.144. That's greater than 0.14. That is a large effect. Fantastic. What if I wanted to do a two ANOVA? So I dealt with fertilizer. Now let's say I want to deal with, let's say I want to do fertilizer and I want to do density. So let's go ahead and let's do fertilizer and density right here. So slightly different code. I'm specifying my first variable here. And actually, interesting. Actually, yeah, I've actually made a little mistake here. So this is dense, and this is not even density here. It's actually block. I believe so, because I believe the DAT. Let me just quickly look here. Yeah, so actually it should be block fertilizer yield. So this is actually block fert. So block fert. Now you see what's going on here? It's basically, this all is basically saying, give me all the two-way, three-way interactions between them. So what does that mean? So I can see, so remember block, there's 4 block sites. So degrees of freedom is 3. Fertilizer, we know there's 3 types. Good. We see this is statistically significant. This is statistically significant. This two-way, or this interaction between block and fertilizer, it is not statistically significant with this p-value here. So that's an important value to kind of see. Additionally, we can look at our values here. I don't think anything changes except for, this. So we can see this is still a large value. So block is indeed large. Yeah, block is large. And we can see here fertilizer is also still large. So we have 2 large effects, block and fertilizer. Fantastic. First, 2 block and fertilizer. What if we want to do a 3-way ANOVA? So what if I wanted to do, let me look at my DAT here. What if I wanted to do density, block, fertilizer, and everything? Well, let's get to it. So if I wanted to do, that's 1, 2, and 4. Let's do 1, 2, 3. Let's do what the full 3-way interaction. So here we go. So density, block, fertilizer, all of them all together. Now, you'll see this little error here. That is because there are not enough data points to do all of, you see we get density and fertilizer, we get block and fertilizer, but we don't get, for example, we get block and fert, we get fert and dense, but we don't get dense and block because we just don't have enough measurements, and we don't have dense, block, and fertilizer. So basically, if it doesn't show up, it means we don't have enough of those measurements. Now, what are we seeing here? Density. Actually, what's happening here? We can actually look at those degrees of freedom. We can set this up here. Density. So let's actually look at, why aren't we getting, excuse me. I'm trying to run this here. So let's look at this. Let's look at our values that we got. Okay, so we got everything here. And if we look at our data set right here, density, our block, our fertilizer, and our yield. Excellent. So let's go through this three-way ANOVA. So we are specifying we want to do density, block, and fert. Those are our variables. And we can see here, oops, it's a little hard to see. So density, we have type 1 and 2. Block, we have types 3 and 4. And then fertilizer, we've got those values here. So you can see here, p-value statistically significant, statistically significant. This is not statistically significant. Now, one of the things that I'm seeing here, now the reason that we're getting essentially, this error, right? Like, for example, we would expect that block needs to be 3. However, basically, we don't have enough combinations and experiments of those 4 block values. So because they're unequal and because there's not enough measurements, Mathematica is really kind of freaking out about essentially these combinations, and it's not allowing it. So it's reducing essentially the number of measurements, and it's throwing out a value. Now, depending on the power, or depending on essentially the signal and the influence of your variable, you still might be able to get away with this. However, whenever you see this error, you should really kind of look through the data like we've done, and basically consider either adding more experiments to make sure that you're really seeing all the values, or kind of like what we've been doing here, you can still kind of get an idea, maybe just not with the full three-way ANOVA, right? Taking different terms. But you can actually see here the block, that dense block is really what's giving you the issue. So that 1, 2, 4. If we're doing 2, 3, 4, so if we're doing block fert, now we're fine, right? This is looking correct. It's actually telling you something a little bit different, that block and fert, again, like we saw previously. So it's really, really important that you kind of quantify essentially those metrics. So if I want to do, for example, 1 and 3 and 4, so if I want dense fert, we're still fine here. So we have enough of those measurements, and it's telling you that those are statistically significant. So really, really important that you dive into the data. Make sure that you're able to calculate and run these Games-Hal tests to determine, are there statistical significances, are there not? And you can kind of see this value here. And we can essentially run with the data set that we've gathered here. So you can kind of see this here. And then you want to be able to calculate that partial eta squared. So that's your 1-way, 2-way, 3-way ANOVA in Mathematica. So fairly straightforward. Again, you just specify essentially the variable type. Make sure you can read that table. Know what the errors are giving you, right? Specify and try to get as many interactions as you can. And remember, it's always variable in the last column in your kind of setup needs to be essentially that outcome. So we'll do another example with a larger data set that has enough statistics, and we'll see you all next time. Thanks. Bye.